Thanks. Thank you, Eric, for that great introduction and for welcoming everybody here. As Eric said, this was in part germinated by a conversation or a series of conversations at the industry board meeting that we had back in May of this past year. But it was also prompted by an increasing realization that there are a number of different departments, units, institutes here at UCSD that have people who are interested in causality, broadly understood, interested in how it is that we come to learn about the causal structure of the world, how we can do it using data, how we can use that kind of information in our science, in our engineering, and in our everyday practices. And so one of the things that I wanted to sort of emphasize right from the outset is the hope that this event today, which is 3 hours or 2 hours and 47 minutes or whatever it is, it will hopefully be the kickoff, the catalyst to many more discussions, many more events. We don't want this to just be a one-off, bring some people together, talk about causality, and then move on. So for those of you who are here at UCSD, please keep in touch, keep watching your email inbox, because we're hoping to have more get-togethers, whether even just things like lunch and learns, so we can learn from one another about what we're all working on. If you're here from industry, please continue to bug Eric a lot and emphasize, because we want to keep having this kind of outreach, keep having this engagement, and to see where there might be opportunities for increased collaboration with our industry partners. And students, this all goes triple for you because it's critical to, I think, understand the ways that causality is and is not increasingly being used in data science and machine learning. So one of the things that I got the short straw task of doing is to give a kind of overview of the topic of causal learning, because this may be, for at least some of you, something that you either haven't thought very much about, or if you've thought about it, you've thought about it as causality is that thing that you have to do a randomized controlled trial. If you're not randomizing, then how can you possibly know causality? How could you ever figure it out? Or if you don't have the domain knowledge of a mechanical engineer, how could you possibly understand the causality, and so on and so forth. There are a lot of assumptions and beliefs about causal learning, about causal knowledge, that I think we've moved beyond from the perspective of data science and AI in the last 40 years. And so my goal is to try and convey at least some of that in the next 15, 20 minutes. If you are really familiar with causal learning in ML in data science, you can turn your brain off for the next 20 minutes because the real insights and innovations I'm going to be handing off to my colleagues up here at this table, as they're going to be doing some 15 to 20 minute research-centered talks after I finish this introduction. Okay. So I want to start just by what might seem like a really simple thing to ask, but I think is important, which is, why should we be thinking about causation in the first place? Why would it matter if we have causal knowledge versus predictive knowledge? So, and the answer is kind of straightforward in some ways when we stop to think about it. If I make observations that enable me to predict what's going to happen, that is not the same as being able to intervene, to act, to control my world, to influence my world. So as a very simple example, I can guess that it's probably pretty warm out today from the fact that many of you, myself included, are wearing short sleeve shirts. But of course, if you are in Pittsburgh or Detroit in February, you can't make it warm by telling everyone to wear short sleeve shirts. Right? So we can predict the weather, we can observe and make predictions about what the weather is or is likely to be on the basis of people's attire, but I can't control the weather that way. Right? So we recognize intuitively that there's a clear difference between observation and causation, and it often matters. So if you're doing work in neuroimaging, you need to be thinking about whether you're trying to diagnose whether somebody is suffering from schizophrenia, that's a prediction task, or are you trying to design novel treatments that can help to alleviate the symptoms or otherwise, I don't want to say cure, but reduce the damaging impacts of schizophrenia in somebody? Or if we're thinking, to stay in the biomedical realm, about cancer, do I just want to predict the progression of somebody's cancer? That's an observation. Or do I want to actually intervene and do something about that progression? And it's not to say, just to be clear, that one of these questions is the right question. There can be different contexts where you want to ask different kinds of questions. If I'm trying to figure out what the needs are likely to be in San Diego County for mental health, then simply predicting whether people are likely to suffer from schizophrenia is sufficient. I don't need to be able to design novel treatments. I don't have to have that kind of causal knowledge. On the other hand, if I'm at the cancer center here and I want to try to help people live longer, I may need to know not only the likelihood of progression, but I may also need to know something about what I can do to change or slow or otherwise alter the trajectory of the cancer. And so these are different. We intuitively know they're different, and yet we can't always get them because obligatory XKCD cartoon for the morning. But as we all know, correlation is not causation. Many of you probably have taken a statistics class. On the very first day, you probably heard some version of this. And the thing is, that's actually right. I mean, these do go together in the sense, as I was talking about with weather forecasting and clothing, they're not the same, even though they do go together. Alcohol consumption is not only predictive of cognitive ability, it causes decline in cognitive ability. Switches don't just predict the state of the lights, they control the lights, right? So we have prediction and causality going together, but of course they do come apart. Senior faculty often have grayer hair. I would not advise my junior colleagues to dye their hair to get promoted, right? That's not a good strategy. And it matters, right? It matters when we make mistakes. So perhaps most famously in the last 20 years has been the discovery that hormone replacement therapy, which while being correlated with heart disease, turns out to be causal in the wrong way, right? But the correlations that we had in the data sets actually suggested that it was preventive of heart disease. In fact, we now have reason to think that it causes increase in heart disease, right? So getting it wrong has real world consequences. And psychologically, it's really hard. This isn't a cognitive science talk, but it is important to recognize that psychologically, we often confuse these. That's where I've got superstitions listed under there. Superstitions are a classic case of we see a temporal correlation. Two things happen at the same time. The Padres finally win, and I happen to be wearing a certain pair of socks, and I go, okay, I must have caused their win by wearing these socks. Well, if only it were that easy to wear a certain pair of socks, and they would actually be good this year. For those of you not from San Diego, you don't understand the angst here right now about the Padres. And so, we can sort of think about it, and here I put correlation in quotes, because really what we're talking about is association, information, between things. That's what we need for classifying. That's what we need for predicting, for giving explanations of why something may have occurred, right? Now I say a causal explanation. And causation is what we need for influencing and acting. So depending on what we need, we're good with predictions and observations, or we may need causal knowledge. And so it's important to recognize that we have to ask the question now when we think about AI, when we think about machine learning, we need to ask ourselves, what is it our methods are actually telling us? Are they actually giving us causal information, or are they giving us merely predictive, we might say, if I'm allowed to use the pejorative merely there. And the short version is actually most of what we use in AI right now is merely predictive. So deep networks, if you just sort of use off-the-shelf deep net, it's a purely predictive thing, which is why you can have the inputs to a deep network be symptoms, and it will predict the disease, even though, of course, the disease causes the symptoms, not the other way around. It's why a lot of efforts to build explainable AI have actually run into problems, because they're really good explanations of how the black box AI system works, but that doesn't tell us anything about how the world works, because it may be getting the causality wrong in its effort to come up with the predictions. And so you might say, okay, but let me go back to that correlation is not causation. Doesn't that mean that we're doomed, right? Why would we even think with AI that we could know something about causality? And in fact, this is, I think, a common view that many people have. It is not uncommon to hear people say things along the lines of, if you haven't done a randomized clinical trial, for example, in medicine, then you can't possibly know anything about the causality. But it's important to realize, if we think about it, this is just a sort of, prompt some intuitions. My colleagues, I'm sure, are going to talk in much more detail. We could think about, suppose we saw an association or correlation between X and Y. What could explain it? Well, perhaps X causes Y, perhaps Y causes X, or perhaps there's some third factor, or any number of other things. Right? And so this is where the intuition about correlation and causation is an accurate one. It is the case that merely because X and Y are correlated, I can use X to predict Y, that doesn't tell me all that much causally, except notice that X and Y are not causes. Now, there's no connection between them, actually doesn't appear here. And if we think about it in the other direction, if I have independence, if there's no connection between X and Y, there's actually not all that many explanations we could give for why we get that statistical phenomenon. And in fact, this is ordinary scientific practice. All the time, people do science, you do science, you look in your data and you say, well, wait a second, hair color is entirely non-predictive of somebody's height, let's say. And you go, well, in that case, why would I think there's any causal connection between them? It's a kind of Occam's razor, simplicity assumption that happens all the time in science. And so what this is supposed to do is just to start to prompt your intuitions that maybe there is a connection between correlation and causation, even if we don't know it, which is that perhaps maybe correlation is a noisy guide to causation, even if it's not equivalent to it or constitutive of it. So if we go back to that original idea and we say, okay, correlation is not causation, but correlation is correlated with causation, then we've got a strategy we could imagine. We could have some sort of way of representing the causal structure of the world, and that we can use to do reasoning and inference about the world, the kind of empirical data that we get. And we could reverse that if we wanted to try to discover causal structure in various kinds from the data, from the world that we have. Right? So we can think about it that if this is right, that there's a connection between the patterns we see in the data and the causality, you can think of sort of reasoning and inference as going this way, and learning and discovery coming back the other direction. And this is the piece, this piece, I think sort of everybody recognizes and is fond of. It's what you do when you have somebody write down a world model or a factory model of a particular process that they know about, and then they draw inferences about what they should see in the data. This is the piece that is perhaps less well known. And there's a number of different ways of approaching it, but I think there's sort of, at a high level, you can think of it as from a big perspective, two different main approaches that people have taken to this kind of causal learning or causal discovery. One, I'm going to label the potential outcomes framework, the other causal graphical models. There are variants on all of these. I am painting with a remarkably broad brush, but hopefully this gives some idea of what we've got. So potential outcomes, this perhaps most famously is connected to Don Rubin, but many others have contributed over the last 50 years to this approach. And the basic idea is that it's grounded in thinking about counterfactuals. So for those who haven't taken a philosophy class or haven't been in one in a while, a counterfactual is basically a statement like, if it were cloudy today, I would not have needed sunglasses. Right? So I'm saying something that's counter to fact. Now, we might, instead of saying that kind of a simple counterfactual, instead say something like, if I had taken that medication, then I would have gotten better. Right? So many of much of the work in the potential outcomes framework actually starts from thinking about things like clinical trials, where I would really like to know, say Sumit got the medication, I'd really like to know if he'd gotten the placebo instead, would he still have recovered? I need to know that counterfactual in order to make an estimate of the efficacy of this medication. But of course, I can't do that. He actually got the medication. I can't go back and create an alternative world in which he got the placebo. And so the potential outcomes framework focuses on these ideas of being able to estimate the parameters, these counterfactual strengths, the impacts from data. And where this comes from very much is epidemiology, clinical trials, econometrics. We see a lot of the use of the potential outcomes framework in that kind of a world. A different approach is a causal graphical model approach, where what you do is you essentially use a graphical network, right, nodes and arrows, to represent the qualitative causal structure. And then what you're trying to do is to estimate that structure from data. So you give me a bunch of data and I say, okay, what are the graphs that could have produced data that looks like those, for example? And here, this approach is more common in areas like genetics, population genetics, psychology, certain parts of the social sciences. And the important moral to take away, at least for the moment, is these are essentially, I could have put a little caveat up there, but essentially these are isomorphic representational systems. Anything you can do in the potential outcomes framework, you can do in the graphical models framework, and vice versa. It's not strictly true for the mathematicians in the room. I will simply note there exist edge conditions, and you have to you have to add a few more assumptions to actually get the isomorphism to hold. But for all practical purposes, they are equivalent. You give me a graphical model, I can translate it into the potential outcomes framework. You give me a potential outcomes model, I can translate it into a graph. But what you can do in one framework might be really hard to do in another framework. And so one of the interesting things that has really, I think, emerged in thinking about causal learning over the last 15 years has been a recognition that we have these two different tools that in some sense could get us to the same place, but have very different strengths and weaknesses. You can think of this as sort of wave versus particle representations, if you remember back to quantum mechanics. For some of you, that may be a helpful analogy. That there, these two different ways you can think about it. It's in some sense going to get you to the same answer, and yet they have very different profiles. So what can we do? At a high level, so if you're going, okay, this is great, but which kinds of problems can we actually solve? We can, of course, solve simple problems. We have methods that if you observe everything that matters, or if you have a linear system, you can infer the causal structure, whether you're doing it through potential outcomes or graphical models. We've got ones that are actually much more complex, can handle more complicated situations. As you would guess from thinking about things like epidemiology and clinical trials, we have to worry about things like unobserved common causes. Maybe the reason that I get the medication is because my doctor looks and goes, yeah, that person seems kind of healthy. Let's make sure to give them the medication because it'll make it look good. This is why we randomize this, so that we don't have these kinds of issues. Or if there's selection bias. If I'm doing my experimental work with college students, and guess what? There are certain things that are going to be true of them merely by virtue of the fact that they're in college. Right? So we have to think about that. So we have systems that can handle that. But we've actually got so many more, right? If we've got partial compliance, you might worry about big data. Well, there are algorithms that can handle over 1 million variables. And variables tend to be the constraining factor here, not the number of data points you have. Data points are pretty easy to handle in causal learning. It's when you get to lots of variables that the computational complexities get bad. And this is, the ellipsis here is deliberate. There are lots of other methods. These are things that people are actively working on, and we will be hearing about some of the latest methods that people are developing with the 4 talks. But there are, of course, many open questions. This is an area where there's a lot of active research to be done. So I already mentioned that we, in some sense, know that we've got these two different tools with complementary capabilities, but yet they have the same power. And so we have to ask, how could we integrate those? So that's a lot of interesting work right now has been coming out in the last 2 or 3 years trying to do exactly that. Or integrating causality into other kinds of frameworks. I mentioned deep nets and said, yeah, they don't give you causality. They don't. They're extracting predictive patterns in your data. But then the question becomes, okay, but could we integrate causality into those? Could we actually take our causal insights and in some sense implement them in the deep network that we've learned? Or could we take a deep network and extract causal information from it? What do we do when we have highly nonlinear systems or other other complexities that arise in our data generating processes? How do we handle multi-level causality? Cases where we want to, for example, say in public health, we might want to ask about the impact of structural racism on an individual's health outcomes. This is something that the NIH is putting a lot of resources into right now, but it requires us to think about causality at multiple levels because, of course, structural racism is not about this individual. The whole point is that it's about a community-level phenomenon. And many more things. Can we use causal information to improve performance in transfer and generalization? I build my model. I want to use it in a new domain. Can I use causal knowledge to enable faster or more accurate transfer? And so on. And so with that, I will conclude my introduction and invite you to sit back and enjoy the next 4 lightning talks that we're going to have from my esteemed colleagues. We are going to, just so people sort of know logistically what we've done with the schedule, is there will be each of the individual talks, and then there'll be time for sort of 1, maybe 2 questions as we're doing the switch over to the next talk. But we've set aside a full hour for discussion, both sort of in panel format, but also more general discussion at the end of of this. So don't worry if you've got a burning question that doesn't get answered immediately after the talk. There will be an opportunity in the last hour to circle back around to that.